Então, boa tarde a todos. Vamos dar continuidade aos seminários em Estatística e Ciência de Dados da Universidade Federal da Bahia. O nosso convidado de hoje é o professor Miguel de Carvalho. O Miguel ele fez doutorado em Estatística pela Universidade Nova de Lisboa, em Portugal. Ele é atualmente professor da Escola de Matemática da Universidade de Edimburgo, na Escócia, no Reino Unido, e é também presidente atual da Sociedade Portuguesa de Estatística. O Miguel já publicou mais de 40 artigos em algumas das mais importantes revistas na área de estatística. Ele atualmente é editor associado do Journal of the American Statistical Association, do Annals of Applied Statistics e do Computational Statistics and Data Analysis. Hoje o Miguel vai falar um pouco sobre valores extremos, um pouco uma parte bayesiana, sobre Lasso, etc. Ele vai falar um pouco melhor sobre o que é que ele vai falar e vai falar sobre detalhes. Então, Miguel, podes começar.
Obrigado, Paulo. Eu desde já queria agradecer pelo convite e queria dizer-vos que é um grande prazer estar aqui com vocês hoje. O mundo mudou imenso, é um desafio dar um seminário online, mas também é uma oportunidade porque é uma oportunidade para comunicarmos de forma mais regular e termos seminários internacionais de forma tão simples como fazer uma ligação através do Google. Antes de começar o seminário, eu gostava de deixar um convite para todos na audiência. Como o Paulo referiu, eu sou atualmente o presidente da Sociedade Portuguesa de Estatística e nós vamos ter o nosso congresso da Sociedade Portuguesa de Estatística que vai decorrer online. E gostava de vos convidar porque é uma oportunidade também para possamos interagir, para que ambas as nossas comunidades estatísticas possam interagir e para que o mundo estatístico lusófono possa ter uma plataforma e um fórum de discussão. E gostava de vos convidar para visitarem o site da conferência. A conferência era suposto ocorrer em Évora, que faz parte do Património Mundial da Unesco, mas infelizmente devido ao contexto pandémico vai decorrer online. Digo infelizmente porque Évora é realmente um sítio espetacular, mas também assim temos a oportunidade de convidar muito mais pessoas a nível internacional e portanto deixo-vos aqui o convite. Portanto, queria, em termos da parte técnica aqui da apresentação, vou então falar em inglês, porque de facto desenhei este seminário tendo em conta que é uma comunicação científica e desse ponto de vista preferia fazê-lo em inglês. So prior to getting started, I would like to start with the title of today's talk. I would like to break into pieces the title of today's talk. So as Paulo anticipated, there will be some ideas related with extreme values in today's talk. There will also be ideas related with Bayesian inference as well as with the lasso, and there's an idea of modeling both the tail of a distribution as well as the bulk. So these are the buzzwords, these are the key ideas underlying today's talk, and this is joint ongoing work with the following colleagues, and in this work has benefited already from several contributors and discussants from including the ones mentioned there, and as well as from other colleagues as well. So let's get started because there's a lot to be discussed here today. And what is this talk about? Learning about what are the drivers of risk is key to a variety of fields, including climatology, environmental sciences, finance, you name it. So, and the field of statistics of extremes has been contributing on that direction with a few univariate strategies that really aim to try to identify what are variables what are covariates that are related with risk. And some recent developments have also been made from a multivariate point of view, including these papers in there, as well as a few other developments, recent developments, which have been made on the spatial setting. Okay, so, and this is the literature on that really tries to identify drivers of risk. And for the purpose of this talk, think about drivers of risk as other variables that could help you to explain risk. And what is the goal here is to propose a Bayesian regression model that fits both the conditional bulk and the conditional tail of a possibly heavy-tailed response. So think of the goal here to design a regression model that attempts to have a good fit for both the bulk and also for the tail. And in a way that really aims to do the following, in a way that really tries to pioneer the development of a class of regression methods that allow for some covariates to be significant for the bulk, that is for the central part of your distribution, but not for the tail or vice versa. Because you see some covariates may be actually significant for the center of the distribution for the bulk, but they may not be for the tail. And so this is what I'll be referring to over today's talk as the bulk, so the central part of the distribution, roughly speaking, and this will be the right tail and this would be the left tail, okay? So the proposed model, the model that I'll be discussing here today, will bypass the need for conditional threshold selection, which is typically a thorny issue in statistics of extremes. And typically, in statistics of extremes, extreme values are oftentimes defined as values which lie above a certain threshold. But the choice of that threshold is not unique, and it has generated lots of research because it is a thorny issue and it is a challenging problem. So our model will bypass the need for that conditional threshold selection. And I would like to highlight the following. So threshold selection is per se a challenging problem, and in a regression setting, you need not only to set a unique threshold, a threshold that would be a scalar, you really need to define a threshold which is a function. So it's even a more challenging problem selecting a threshold in a regression setup. And our proposed model will aim to model both the conditional bulk as well as the conditional tail. That is conditional on a certain value of the covariate. We would like to have a model that tries to fit both the bulk and the tails, but that depending then on the value of the covariate, that it's the shape of the density keeps moving along with that covariate. Okay, so now on top of this, we would like this model that I'll be discussing here today to be directly tailored for variable selection in an extreme value framework. Okay, so let me get you into the basics to get started in terms of how people address these in an extreme value framework. So, and there the interest is typically on modeling the most extreme observations, totally disregarding the central part of the distribution. And usually the effort centers on modeling the tail of a distribution using either a generalized extreme value distribution on a block maxima framework or a generalized Pareto distribution when you are in a peaks over threshold setup. Reference on these are, you can see more about these two frameworks on these monographs. And of course, it goes without saying that then many observations are simply disregarded using the latter approaches, and that the choice of the block size and threshold are far from straightforward. On top of this, in many situations of applied interest, it would be ideal to model both the bulk of the data along with the extreme values in a regression framework. And that's what we're aiming to do here today. Our model will build over Papasatopoulos and Ton, 2013, as well as over Navu, who proposed an extended generalized Pareto distribution to model jointly low, moderate, and extreme observations without the need of threshold selection. So this distribution will be key in terms of the construction of our model. It will be the starting point for it. Of course, other interesting options for modeling both the bulk and the tail of a distribution include, for example, extreme value mixture models, which has been an area that is also very, very interesting. I'm mentioning here a few references, and there has been some work from colleagues in Brazil in this direction that I'm aware. So I'm not citing all papers on this direction, but this is certainly another interesting approach as well. So the model that we'll be proposing in here today can be regarded as a Bayesian Lasso-type model for the conditional bulk and tail. And let me tell you a bit more about the Bayesian lasso and what it aims to achieve. So the Bayesian lasso was introduced by Park and Casella in 2008 in a paper at JASA, and it is a Bayesian version of Tibshirani lasso. Okay, so here is Lasso 101. Think about least squares and think about simple linear regression. And what the frequentist lasso aims to achieve is the following. So you're aiming to conduct both estimation and variable selection all at once. And you do that by essentially constraining the optimization problem that leads you to the least squares estimator with a certain shrinkage factor that gets you to add on top of estimation also to include the idea of a variable selection. So it's as simple as that. It's almost like ordinarily squares type of estimator, but where you constrain also the optimization in order to shrink some of the coefficients towards zero. Okay, right. So as I've anticipated, it is simply a regularization method that is naturally tailored for variable selection, shrinking some coefficients and setting others to zero as well. Okay, and then you see, this is the lasso, and this is the geometry underlying the lasso. So this would be the type of constraint that would be generated via the lasso. So, and it is an L1 type of penalty that gets you that you can use, but you could also wonder, why don't I use an L2 type of penalty in my objective problem, in my optimization problem? And you could do that, and that has a different name that is known as ridge regression. And you could use a different geometry for the penalization, and then the method gets a different name depending on the type of penalization that you use. Okay, for the purpose of today's talk, I'll be focusing in terms of L1 penalization, which from a Bayesian perspective could be seen also as a Laplace type of prior. It could be induced by a Laplace type of prior. What do I mean by that? I mean the following. I've just told you that the lasso essentially corresponds to a constrained optimization problem, similar to least squares, as I've mentioned earlier. Okay, so what Park and Casella did was to ask what would be the prior whose posterior mode, you see the mode is again the argument of a maximum, what would be the prior that would give you, that whose posterior mode would give you exactly the same solution as that constrained optimization problem that leads you to the lasso. So it's a different perspective, but it's getting you essentially the same thing. So, and what happens is that the Laplace prior is the one for which whose posterior mode ends up corresponding to the solution that you get with the lasso. Okay, right. So the Bayesian take on this is to really rethink the constraint optimization problem via a certain prior, a certain shrinkage prior to get you what you need. Right. Okay, so as we clarify below, our model has links with quantile regression as well. Indeed, by modeling both the conditional bulk and the conditional tail, our model bridges both quantile regression with extremal quantile regression, and as a byproduct, I would claim that this will also contribute to the literature on Bayesian inference for Pareto distributions. Okay, I've offered you a snapshot, an overview, a roadmap of what we aim to achieve, as well as a crash course on related ideas. So to give you the background in order to understand our developments. What I'll do next is to introduce our extreme value Bayesian lasso, and then I'll move towards a real data application as well as some closing remarks. Okay. How do we do it? As I mentioned earlier, the starting point is this extended generalized Pareto distribution. And I would like to invite you, we're entering more into the technical part of the talk, or the part which is related with our contribution. I would like to invite you to ask questions as I move along in case you have questions as well. Okay? Okay. So we're getting started with this extended generalized Pareto distribution. So this is the starting point. And what is an extended generalized Pareto distribution? It's simply a composition of two functions, essentially where your H is the generalized Pareto distribution, whose distribution function looks like this, with another function G, which is known as a courier. Okay, so think of this courier function as a function that is distorting your generalized Pareto distribution, but it should leave the tail of that generalized Pareto distribution completely intact, in a sense. Okay, so this is it. This is the class of extended generalized Pareto distributions. So there's a parameter G, if you will. You can really think about G as a parameter. It's a function, okay? And essentially what you get out of this is this composition that gets you the generalized Pareto distribution tilted in a way. Okay? Now, in terms of these generalized Pareto distribution, to give you context as well, Xi is the so-called extreme value index, and when Xi is positive, you are in the domain of heavy-tail distribution. So essentially, this Xi, which is a shape parameter, is the one controlling the rate of decay of the tail. So the larger the Xi, the heavier the tail, in a way. Whereas if you get Xi to be equal to 0, you would be in the so-called domain of attraction of a Gumbel distribution, and with negative Xi, you would have a tail which would be quite light. For example, uniform distribution would be in that domain of attraction. So think of this shape parameter as a parameter that is controlling the rate of decay of your tail. And Xi being positive, it's really when you have heavy tails. Okay, so, right, this is what I've anticipated. So, and this G, the one that appears here, okay, this G, this parameter G is a courier. And you might ask, as me, if you're not a native speaker, what the hell is a courier? This is a courier. And it makes sense. And it makes sense if you go back and if you think this is exactly doing what the mathematical object, what I told you the mathematical object is doing. So G is transporting part of the mass elsewhere. So it's transporting part of the mass of the generalized Pareto distribution elsewhere. Okay. Of course, this does not give you the mathematical definition of what a courier is, but this is what literally it would be understood what a courier would be. Okay, so mathematically, what would be the definition of courier? So G is a courier if it obeys the following assumptions. So there's three limits that it needs to obey. So it's a mathematical object that needs to obey these three assumptions. And I'll comment on these assumptions in a second. I want to anticipate that one of these assumptions will be leaving you the. Remember that I promised you that we would want to leave the tail of the generalized Pareto distribution intact. So part of these assumptions is doing that, whereas part of the other assumptions is concerned with the behavior of the book. Let me give you a bit more of detail. So assumption A, the one in here, is essentially telling you that you will be having a Pareto tail. So whereas assumptions B and C will ensure that the book is driven by the courier. So the courier is the function essentially that is driving you the book, but it's not touching on the tail. Okay. In more detail, to give you a bit more of background on this. So assumption A will imply that this ratio of limits will be equal to a constant, which is known in extreme value statistics parlance as a tail equivalence condition. Okay, what are the consequences of that? There's an interesting consequence of that because it is well known since Sidney Resnick paper in 71 that tail equivalence essentially will imply that both these guys will be in the same domain of attraction, which essentially means that the extreme value index that I see on my generalized Pareto will be the same index I should see on my F here, on my extended generalized Pareto distribution. So this is a consequence of this. Okay, so how do we go about modeling? So remember that I told you that G is a function. We could model it really as a function, but for parsimony reasons, we'll be focusing on modeling G using a parametric class, so that there will be, essentially G will be indexed by a certain parameter kappa that lives in Rk. That's the goal in terms of the next slide. So as an example, this is what we're referring to as a parametric courier. So it's essentially this power function. And in terms of specification, in terms of first version of the model, this is it. So it's simply doing this composition where you essentially have this G of kappa indexed by X. So along this parameter kappa, which is controlling or having its main influence on the bulk. So we're indexing that with a covariate, and essentially kappa x is a vector function with components given by inverse link functions in here. Okay, I just want to go back to some notation you may have not noticed, and that will be important. So there's two pieces of notation in here that I'll be using. So this curly G, when you see this curly G, it's simply the space of all couriers. That is the space of all these functions. Whereas here, this notation will be simply used to define, to denote, an extended generalized Pareto distribution in general, with these three parameters kappa, sigma, psi, and with the corresponding G. Okay, right. So this is, keep this in mind. This is the first version of the model. It is this composition that you get with between G and H, and where you simply have, this is the first version of the model. This is a bit naive for now. You're just allowing that parameter kappa to depend on your covariates. Okay, right. So G itself will have to be in the space of all courier functions for each value of the covariate, so that this is well defined. And these are the corresponding regression coefficients for this model. Note that for now we're not allowing sigma and psi to depend on covariate X, but we'll be changing that later on. Okay, let's see examples. So again, with the power courier and with an exponential link, you get the canonical embodiment of the first version of our model, which is obtained by specifying this canonical courier function, and where you're saying that kappa of x is given using this link, exponential link. Okay. Other options would be available by mimicking some of the well-known couriers for the extended generalized Pareto distribution, such as the beta courier. Okay. And this would be still another variant. So there's as many possibilities as G's you can think that would obey assumptions A to C. Okay, note that this specification, the one where we have the composition between G and H, will imply that the corresponding conditional quantiles are defined in this way. So you can write down the conditional quantiles as a function of both the courier and kappa of x, and the expressions look like this. So and that already allows us to anticipate that the first version of our model can be regarded as a model that is aiming to bridge quantile regression with extremal quantile regression, in the sense that it offers a way to model both moderate and high quantiles as well. Just to remind you that quantile regression is essentially a regression model for the conditional median, where you are allowing for the slope to change along with the corresponding quantiles as specified in here. Okay, so note that we're not setting up in here any linear specification. This specification it follows naturally from the extended generalized Pareto distribution. And it will allow you to extrapolate beyond observed data into the tail of the distribution. Okay, I promised you we would be talking about Bayesian lasso. Let me deliver now on that. I want to tell you how do we learn about this model from data. So let x, y, yi be a random sample from your joint. We propose the Bayesian lasso type specification for the model above, so to regularize the log likelihood. The idea is simply to do the following. So let's specify this G, and so that the likelihood is simply of this type, where beta is the vector of regression coefficients, this H is the density of the generalized Pareto distribution, and G is simply the derivative of the courier function. So the likelihood will be written in general in this way, okay? Now, in a Bayesian context, as I've already anticipated the idea, the lasso can be interpreted as a posterior mode estimates when the regression parameters have Laplace priors. Remember, frequentist lasso is all about a constrained optimization problem, one that almost looks like least squares, but where you have to put a penalty. And the Bayesian take on that is essentially to have a posterior mode that delivers you exactly that. And for that, we need Laplace priors. Okay, so that's essentially what a Laplace prior is for each of the regression coefficients. If you want to learn more about this, have a look at the references we're mentioning there. Now, you could ask, what about this lambda parameter? And in terms of that, we're just using here standard option gamma prior on lambda square. Okay, so first version of the model, it's as straightforward as this. So there's a likelihood, which is EGPD. There's this parameter kappa, which is controlling the bulk of your distribution, and essentially the priors look like this. Now, of course, in practice, some covariates can be significant for the bulk, but not for the tail. And this is one of the key motivations actually for our model. So how do we go about adapting our model so to accommodate for that? What we do is we extend the previous specification by also allowing parameters underlying the tail to also depend on a covariate. Specifically, this is how it looks like. So this is the specification of interest. It's again the same design. It's a composition of a courier function as well as a generalized Pareto distribution, but actually in this case a conditional generalized Pareto distribution. There's one trick we'll have to do, which is reparameterizing that conditional generalized Pareto distribution. I'll tell you in a minute why, but that is very important that we do that. Otherwise, it's very challenging from a computational point of view. Okay, so this is essentially it. So this f, this conditional f, is essentially our model. Okay, and as earlier, we're also considering your inverse link functions for both nu and for psi. Okay, so that means that there are three parameters that are indexed by covariates now. One is accounting for the bulk, that's kappa. There is another parameter which is controlling the magnitude of the extreme events, as well as how they depend on x. And there's another parameter, nu of x, which is telling you something about both the scale of the extreme events as well as their magnitude. Okay, so there are three regression pieces here: kappa x, nu x, as well as psi x. Okay. Okay, so this is the canonical full model. So you set up, for example, kappa to be exponential x transpose beta, nu to be also x transpose alpha, and psi to be of this type. Okay, this would be the full version of the model. There's the likelihood is again an extended generalized Pareto distribution, but note that now we're also allowing the scale and the shape parameters to change along with the covariate. We're properly specifying also regression models for those. And in terms of priors, again, we shrink everything by using Laplace type of priors. Okay. I told you that there's a need for reparameterization. And why? Well, first, we didn't reparameterize. We were fitting the model, and we realized that it was computationally not stable. Then we found that actually similar evidence was already provided by Chavez, Demela, and Davison in a different setup, as well as by Cabras and Castellano in a different but related setup in a generalized Pareto setting. So that means and that was important. After realizing that, we realized we really need to have a reparameterization. The next question was, would all reparameterizations be okay? And no, because we really would like to keep the parameters for the bulk and tails completely separated. Whatever reparameterization we were doing, we wouldn't want to get these effects to be mixed, because we really would like to separate these effects. And why? Because we really want to understand what covariates are important for the bulk and tail, and thus we cannot mix the parameters for conditional bulk and tails. In other words, we're simply looking for reparameterizations of this type, where kappa is untouched or only would become a function of kappa, and where sigma, the scale parameter, may become a function of both scale and shape, or where shape may become a function of scale and shape, but we really don't want this guy to be a function of kappa. Otherwise, it would be difficult to trace what matters for the bulk and what matters for the tail. Okay. The other point, the other remark I would like to give in terms of reparameterizations is the following. So in terms of the Fisher information is key when you want to have a parameter orthogonality, which would be desirable from a computational point of view. But that requires, as you might know, that requires that you compute the Fisher information matrix. And that's not good, because the canonical extended generalized Pareto distribution is actually a particular case of the so-called generalized failure Pareto distribution. And let me show you the Fisher information matrix, how it looks like in that case. I'll be quiet. That's it. This is just one of the entries. It's an entire page. It's not the way to go. It's really not the way to go. So what we've done then was how to design a reparameterization that is good for our purposes, and this is this is what I'm answering next. The reparameterization that appears here is known to be orthogonal for the case of the generalized Pareto distribution, but it will only be approximately orthogonal for the extended generalized Pareto distribution in a neighborhood of kappa equal to 1. Why? Well, because when you have kappa equal to 1, you actually get back to the generalized Pareto distribution function. So, but how do we really see the details on this being approximately orthogonal for the extended generalized Pareto distribution? We see it as follows, at least from an heuristic point of view. We compare the likelihood of the canonical extended generalized Pareto distribution with that of the generalized Pareto distribution. Here is some notation to keep in mind. L will be for the EGPD, whereas when you see a star, it will be for the generalized Pareto distribution. Okay. To make this argument easier, I'll concentrate on the single observation case, but the derivations below hold more generally. That is, okay, the idea is you want to relate the likelihood of the EGPD with that of the GPD. It works as follows. So the two models have, remember that extended generalized Pareto distribution as this extra parameter, okay? Remember that. So essentially what you can write is these like two likelihoods relate as follows. L of psi equals L star of theta plus this remainder term in here. Okay, that means what? That means that in a neighborhood of kappa equal to 1, essentially we'll be having these two guys to be an approximation to another. Okay? Right, and actually what happens is that the similar relation still holds for the corresponding Fisher information matrices. So I have to be careful in here because one of the matrices is actually larger than the other. What I'm mentioning is that this guy in here, this I of theta, that is when you consider the entry in the Fisher information matrix that just corresponds to the part related with sigma and psi, that's essentially the same, almost the same as this guy in a neighborhood of kappa equal to 1. Okay, and that can be seen essentially by writing down things. That's essentially it. You just write I of theta, the block I just mentioned, and after you realize that, you actually see that for exactly for kappa equal to 1, all these would disappear, and you would be essentially back to the information matrix for a generalized Pareto distribution. Okay, despite the fact that the reparameterization that I'm mentioning here is only quasi-orthogonal, our numerical experiments indicate a satisfactory performance. Certainly, if there was any way to build a more clever reparameterization, certainly it would be welcome, but this was one that numerically, at least, we have good indication that it works nicely. Okay, this is just a proof of concept. There's more. There's a paper ready at arXiv on this. I'm skipping a few details in terms of numerical studies we've conducted. This is just a proof of concept. One example to offer you a flavor of how it would look like. Left is the true, and right is the corresponding estimate in a single run experiment. And beyond this, we've also assessed in terms of the significance of the corresponding regression coefficients. This fits the time presenting there. It's just an heat map of the conditional density. Okay, but we also have assessed performance in terms of regression coefficients. Okay, Paul, I know that you want me to end at some point, so I'm just offering you now an idea on how this works with data. Is that okay?
Yes, sure. You have maybe 5 or 10 minutes. That's okay.
Cool.
Up to 10 minutes, it's perfectly fine.
Excellent. Thank you, Paul. Okay, I want to tell you now what we can see with this, because I've been telling you about the theory, the methodology, it's a simple solution for a problem that I personally regarded as interesting from a methodological point of view, but what can we do with it? Okay, and now let's illustrate how it works in a climatological illustration with data from Funchal, Madeira. So Madeira is in Portugal, and it's part of Portugal. It's in the midst of the Atlantic Ocean, so it's an island with a volcanic origin, roughly 1,000 kilometers from the south of Portugal, roughly. And Madeira suffered a variety of extreme rainfall events over the last 2 centuries, including flash floods of October 1803, where you had 800 to 1,000 casualties, February 2010, 45 people death toll. And this has been documented and studied by people who really know the field, and these are climatologists. And these violent rainfall events are often also followed by landslide events that include debris, earth, and mud flows. So it's really not just the flash floods, but there's also consequences of the flash floods, and these are really terrible as well. Okay, so this is Madeira. You would be outside of my screen here in Bahia. So that's where Madeira stands. Okay, and this is just one picture from Madeira. You can find these on internet and other pictures as well. For me, this photo is really like, I've actually been on this street once, and when I saw this, I was really thinking, wow, this is really this is an extreme event. Okay, and this is another. You see the debris then after the flash floods. So it really has then an impact, clearly. Okay, we have data for this real data application that was gathered from NOAA, and the variables are total monthly precipitation, as well as the following potential drivers for extreme rainfall: AMO, ENSO, NP, PDO, SOI, as well as NAO. Okay, so these have been examined by climatologists and have been evaluated as potential drivers for extreme rainfall, although I must stress that climatologists, at least in those papers, have not been using directly methods for extreme value statistics, which means that their methods will not be tailored to see beyond the data, extrapolating into detail. So keep that in mind as we move along. In any case, those have been identified as potential drivers. Okay, sample period that is from 1973 to 2018. Okay, and these are monthly precipitation levels. Okay, so the climatological literature claims the following: for North America, ENSO, PDO, and NAO, they seem to have some effect governing the occurrence of extreme rainfall events. That has been mentioned at least on these papers. But for example, if you go to the UK, NAO might impact occurrence of extreme rainfall events, but at least in this paper by Brown, no influence of PDO nor of AMO was found. Okay, so you see, North America may be PDO, yes, but not for UK. NAO seems to be present on both of these. Of course, these are different climates, but it's interesting to find as common point PDO here on both. Now, the many peculiarities surrounding Madeira climate, such as the Azores anticyclone, Canary Current, as well as the Gulf Stream, along with the negative impact that flash floods and landslide events produce on the island, motivate us to ask the following question. Are these drivers, the one I've mentioned earlier, relevant for explaining extreme rainfall episodes in Madeira? Because it's a climate that is in the middle of the Atlantic Ocean, so are these drivers relevant? Also, are these drivers also relevant for moderate rainfall events? Yes or no? And this is the analysis. So we're really trying to separate significance for the bulk from significance for the tail, and what we see is the following. So note here that ENSO and NP, they seem to be the ones that are more relevant from the point of view of the book. But let me also go here to the tail. ENSO, which I've highlighted earlier, it's there, definitely. It's definitely there. But surprisingly or interestingly, it's also perhaps relevant for the tail. But look at NP. So NP might not actually have any impact in terms of the magnitude of extreme rainfall, but it actually might be the most important one for explaining moderate rainfall. Have a look also at NAO, which from the perspective of the tail, it seems to be one which is quite interesting in the sense that it seems to be related with extreme rainfall events. But if it has an effect on the bulk, we can't see it clearly with this inference. Okay, so what matters for explaining extreme rainfall events might not matter for explaining moderate rainfall events, and this is one methodology to try to contrast such effects. This is just one chart to assess. These are the so-called randomized quantile residuals. Think of this as a QQ plot, but it is a QQ plot for our model. And what this seems to suggest is the following. So overall, the fit is okay. The fit is not superb for higher quantiles. I think of this model more. The added value of this type of analysis will be more in terms of contrasting what is significant for the bulk and the tails, and perhaps from the point of view of prediction, I still would keep using models for the extreme values only, at least if the interest was on just assessing the risk of a certain extreme event. Okay, I'm ready to conclude. I've introduced a Lasso-type model for the conditional bulk and tail, and the proposed model will bypass the need for threshold selection, models both the conditional bulk and the conditional tail. It is tailored for variable selection, and it pioneers the development of methods that allow you to track if some covariates are significant for the bulk, but not for the tail, and vice versa. And the proposed methods have been illustrated to track drivers of moderate and extreme rainfall in Madeira, Portugal. I just want to conclude with pointing to some directions for future research. A version of our model that includes a point mass at 0 would certainly be natural for a variety of contexts, such as when you also want to model long periods without rain or droughts. And semi-continuous responses are indeed common in practice, and that model could be used beyond rainfall, certainly. I want to also comment on the following. If you want more flexibility, we could certainly endow the model with further flexibility by resorting to a generalized additive model where the smooth functions for each covariate is modeled using B-spline basis functions. but that would require penalizing in a different way. We would have to shrink regression coefficients towards 0. Finally, there's the question in terms of flexibility, in terms of the courier function. We could put a prior directly on g of x. There's a potential way to do it using Bernstein polynomials on which I could give details in case someone is interested. Thank you so much, and I look forward to your questions. Thank you.
Muito obrigado, Miguel. Vou falar em português, eu acho que a maior parte das pessoas falam português. Agradecer novamente o Miguel pela apresentação. Nós somos da mesma turma da nossa graduação, entramos juntos na graduação e fizemos mestrado, doutorado, agregação, mais ou menos ao mesmo tempo. Então é um prazer ter-te aqui connosco. Vou então abrir para perguntas. Não sei se alguém tiver alguma pergunta, pode ou escrever ou pode ligar o microfone e fazer a pergunta. Então, enquanto as pessoas pensam, Miguel, eu estou aqui a pensar de que forma é que imagino que tenhas feito o código para isso, imagino no R talvez. De que forma é que a quantidade de dados ou a dimensão dos dados pode afetar a performance, quer de convergência, quer computacional?
Essa é uma excelente questão. Eu não tenho detalhes em relação à parte computacional, mas nós temos código JAX e o código JAX é relativamente curto para ajustar este modelo. Outra possibilidade seria que não exploramos, mas seria escrever código através do stan e tenho alguma curiosidade em o fazer até para avaliar o ponto da reparametrização. Da nossa experiência computacional, aquilo que entendemos é o seguinte, é que em termos de performance, em termos de quantidade de dados, diria que a partir do momento em que temos 300, 400 pontos na nossa nuvem de pontos, já temos um ajuste bastante razoável. Eu diria o seguinte, o desafio maior não está na dimensão da amostra. O desafio maior acaba por estar precisamente em termos da reparametrização. E aí, de facto, levou-nos algum tempo a entender o ponto da importância da reparametrização. No início, quando tivemos a primeira versão do modelo, corria tudo bem. Quando digo primeira versão do modelo, digo a versão que só o K é que dependia do X, corria tudo perfeitamente. E à medida que fomos acrescentando os parâmetros referentes à cauda, entendemos aí que claramente ou a nossa reparametrização era ortogonal ou quase ortogonal, ou então tínhamos muita dificuldade. Números que eu não reportei aqui, mas que sabemos. Os effective sample sizes, que são uma medida de facto quantas iterações é que se está a mostrar a posteriori, eram extremamente reduzidos quando não fazíamos a reparametrização. Portanto, quando digo extremamente reduzidos, digo, por exemplo, de um posterior sample de 1000, aproveitavam-se 20. Quer dizer, digo, aproveitavam-se 20 em termos do effective sample size ser 20. E o que significa que levávamos muito tempo a aprender do modelo, tínhamos de aumentar drasticamente o número de iterações e mesmo assim os resultados não eram tão satisfatórios como desejávamos. A partir do momento em que mudamos a reparametrização, tudo mudou. Portanto, o desafio de facto esteve mais do lado da reparametrização do que em termos do número de dados. E, obviamente, se fosse um modelo só para caracterizar os valores, só para caracterizar a cauda, aí como só se acaba por utilizar os valores acima de um determinado threshold, aí esses métodos vão necessitar de mais dados.
Obrigado, Miguel. Um dos nossos alunos, o José Guilherme, ele parabenizou pela excelente apresentação. Perguntou se o código está disponível e qual o software que usaste.
José, é uma boa pergunta, eu já respondi parcialmente, mas é uma boa pergunta. Nós incluímos no material suplementar uma versão do código, e o código foi escrito em JAX. Na versão no archive, eu já não tenho a certeza absoluta se o material suplementar se foi anexado à submissão, mas vamos submeter em breve uma outra versão do paper para o archive, e nessa versão, que será a versão final, oxalá, certamente ficará. O paper está, entretanto, a ser submetido para uma revista, e portanto, vamos disponibilizar uma versão nova do artigo, e se não está já no archive, certamente que estará nessa fase. Mas está no material suplementar, incluímos no material suplementar.
Certo, obrigado. A Lígia está a dar os parabéns pela apresentação. Mandar um cumprimento aqui para a Lígia também, já não vejo há tempo. O Paulo Henrique e a Lília são dois colegas do departamento, também estão a dar os parabéns. E não sei se alguém tem mais alguma pergunta que queira fazer ao Miguel. Não, parece que não. Então é isso, Miguel. Muito obrigado novamente pela disponibilidade e agradecer a todos os que participaram aqui nesta hora de almoço. Aqui foi entre a 1 e as 2, que é a hora de almoço, então nós, quando temos algum convidado da Europa, tentamos fazer um pouco mais cedo, que é para não ficar aí em cima muito à noite. E daqui a 3 semanas, normalmente nós organizamos estes seminários a cada 3 semanas, então daqui a 3 semanas, provavelmente na quarta, teremos um novo seminário, iremos enviar a informação, entretanto. Então, muito obrigado novamente, Miguel, obrigado a todos e boa tarde para todos.
Obrigado a todos. Muito obrigado.